update its position to a more accurate position, as well as the fact that it tricks the node into thinking it has a very low error when in fact it does not. The last type of attack we look at is the oscillation attack. So here is actually two movies, if they play here in a second. Yes, and okay, they're actually playing on the screen. And you can see that under the no attack scenario, the system is actually able to form a definite structure. So groups that are close together actually have low round trip times between them, and you can kind of form clusters depending on where their nodes are located. However, under the attack scenario, we can see that the nodes just kind of swarm around without any definite structure. So besides losing this visual structure, the system itself loses the ability to accurately predict the round trip time between nodes. So not only can we see the effects of the attack visually, but we can actually see them on our two metrics. We can see that from the left-hand side, which is a system prediction error, and the right-hand side, which is a relative error, that as the number of malicious nodes increases, the effect of the system, the performance of the system becomes worse. So a small percentage of attackers is actually able to generate double or triple the amount of system prediction error and relative error. So there's been some previous work on creating robust virtual coordinate systems. Most of the work is actually focused on just creating low-error virtual coordinate systems that work in benign environments. Other work has shown that virtual coordinate systems are vulnerable to attack, and there's been one or two previous solutions. Some of the previous solutions have looked at the triangle inequality, which is often violated in the internet and not practical to deployed systems. Others use trusted network components or extra sets of nodes in communication. And we wanted to avoid these types of solutions, which actually induce things like actually adding structure or added fixed components to a network, or added extra overhead to what is supposed to be a low overhead system. So our goal was to add robustness by three main points. Is first, to reduce the likelihood of making a poor change. Two is we wanted to maintain the decentralized structure. And three is we wanted to maintain low communication overhead, similar to the design goals of the virtual coordinate systems themselves. In order to do this, we will use local decisions based on local and remote data that's already reported in the system. And the mechanism we use is anomaly detection, so it's multimetric correlation and statistical outlier detection using both spatial and temporal outliers. We want to reduce the number of incorrect changes, and we do this by detecting inconsistencies in the reported data. So we look for inconsistencies with respect to what other nodes in the neighbor set have reported. So for example, if we have a neighbor set of size 64 and say 62 of these nodes are reporting a low error and very little variability in the coordinates, and 2 of the nodes are varying wildly, these nodes will be detected as being inconsistent and possibly malicious and avoided for use in actually updating a node's coordinates. Second, we look for inconsistencies between reported metrics for an individual node. So for example, if a node says it has low error but it has a very variable coordinate, these are inconsistent with each other, and thus the update will be considered malicious. And finally, we look for inconsistencies with the past history. Does what the node is reporting now remain consistent with what was reported in the past? So for a little more detail on spatial outlier detection, we look at using local and remote data already used in the system. So we use RTT, the remote error, and the change in the remote coordinates in order to determine if a node is a spatial outlier or not. We do this by collecting a set of samples, so we use the most recent 64 samples, and by using this data set we compute a centroid. So here on the graph we can see the centroid is denoted by the red triangle. And then the distance from the centroid is computed using the melonovis distance, and anything that's beyond the set threshold here denoted by the ellipse is determined to be a malicious update. Anything within the ellipse is actually denoted as a benign update and used to update the node's coordinates. The reason we use the melonovis distance is it's good at detecting multiple attributes. It takes into account both the variance and covariance of the attributes. So in other words, attributes that have high variance receive less weight than those that have a low variance. So things that are more stable should be accounted more highly in whether or not something is malicious. And finally, it takes into consideration the correlation between the attributes. And since we have an environment that has multiple attributes that are correlated, this is a perfect type of distance measure. For our temporal outlier detection, we actually use a 5-tuple. We use a little bit more data, and we use the RTT, remote error, local error, the change in remote coordinates, and change in local coordinates. And for each of these, in order to avoid having to store the entire history of a node's interactions with each other, we simply store a temporal centroid. And what this consists of is the mean, the standard deviation, and the sample count. And so for each interaction the node has with other neighbors, it maintains these 3 metrics. And then we use a simplified melonovis distance in order to determine if the update is an outlier or not. And so to put it all together, quite simply, if the tuple is not a temporal outlier and it's not a spatial outlier, well then the data is used to update a node's current coordinates in air and is included in the data set that is used to calculate the spatial and temporal centroids. Otherwise, it is rejected as being potentially malicious and is not used in future calculations. So to actually look at the effects of our mitigation techniques on the system, here we look at a various percentages of attackers using a spatial threshold of 1.5. And we can see that our mechanism is actually able to mitigate the attacks. If we look at the blue and the purple triangle lines, we can see that with no detection, the relative error is around 2.5 times what it is under no attack. So this means the system is operating 2.5 times worse than it was. And then with our detection technique, we can see that the relative error returns to just a little bit above 1, even when 30% of the network is malicious. What's also interesting to note is that if we look at the red and the blue lines, which are the 20% attackers, if we look at the 20% using our detection technique, we can see that the relative error is actually under 1. So it means with our detection technique, we're actually able to help the system return to performing actually better than it was under the benign scenario without our mechanism. So not only are we able to avoid the malicious updates, we're able to avoid high error benign updates that would otherwise cause spurious changes in the coordinate system. So not only are we able to tolerate the malicious nodes, we're actually able to tolerate malicious coalitions. So what this means is that even if the malicious nodes are working together, our mechanism will still work. And so approximately 30% of the network needs to actually work together in order to subvert our defense mechanisms. As we can see from the chart, we can see that approximately 20 nodes out of a neighbor set of size 64 need to be malicious in order to have any random update bypass our outlier detection technique. And so this actually converts into about 30% of the network. So just a quick summary of robust network awareness. We've seen that virtual coordinate systems provide a lightweight solution for creating network-aware applications. The virtual coordinate systems are vulnerable to malicious activity, and that outlier detection can be leveraged to add robustness to the system. So the second component we'll actually look at is robust adaptation. And so what adaptation allows peer-to-peer systems to do is to be able to change their structure, change their topology, change the way they function in order to better service the system or service the user and to maintain certain service guarantees. For example, if you're watching TV and you need to maintain a certain amount of bandwidth, adaptivity allows the network in order to change its structure to make sure that the user is always receiving enough bandwidth in order to maintain a smooth signal and not have a choppy playback. In order to better look at adaptation, we'll look at a specific type of system and the adaptations that it can actually contain. So we look at an unstructured multicast overlay network. So what this is basically a physical network, and on top of that is built a mesh control plane in which information is distributed about the control plane, about the latency, about information about the network. And using this mesh control plane the information provides, on top of that is built a tree-based multicast. And this tree is adapted in order to maintain application-specific performance. So in this case, it's streaming video, so it's trying to make sure that every receiver receives 480 kbps. Since it's unstructured, it's self-organized. There are no constraints on who can be neighbors of who can be a parent, who can be a child. And each node simply maintains a parent, a peer set, as well as a routing table or the children or who it's sending data to. In order to allow the tree to adapt, metrics are collected by the nodes through 2 techniques. The first being a passive observation of the performance from the source. So a node records how much data it's receiving and the information it's receiving from the source, any data the source is giving it, as well as it periodically probes neighbors or peer nodes around it in order to receive their information and see how they're actually performing. It does this in order to see that if a peer is performing much better than I, then maybe his parent is somebody I should ask to be my parent and receive better bandwidth. So once these metrics are actually collected, they're used to compute a utility function, and then based on the utility function, the node will decide whether or not to actually change its parents. So we use ESM, or end system multicast. It's a mature multicast system. It's been used to broadcast things like conference keynotes and other things like that. So the metrics it actually uses is bandwidth, latency, round trip time, loss rate, and the degree. In order to ensure that there's data quality, especially from benign errors, it uses things like data sampling and data smoothing in order to address variations in the metrics, and it uses dampening and randomization hysteresis in order to address instabilities and avoid things like flapping back and forth rapidly between parents or changing routes. In order to actually improve the decision quality that a node does when it's actually deciding whether or not to change its parents, it actually uses several utility functions with a variety of inputs in order to try and find the best decision to take. Once again, it's important to note that the accurate interpretation of these metrics and the observations that they infer are critical to the response of the system. And so there are actually multiple types of attacks that can actually exploit these adaptive mechanisms, and these classifications, or these attacks, can be classified in three broad classifications. First being the attraction attack, repulsion attack, and disruption attack. And we'll look more in detail at the attraction attack. And not only these attacks affect the structure of the system, but they can also be used to facilitate further attacks, such as data dropping or analysis of the structure of the system. So the attraction attack is an attack in which a malicious node tries to attract more children in order to have a more important place in the tree. So the more children a node has, or the higher it up is in the tree, the more traffic it controls of the entire system. So for example, if we look at the images on the right-hand side, initially the malicious node is one of the leaf nodes of the tree. It's connected at the bottom of the tree and has very little influence over the tree. However, once it performs the attraction attack, we can see that it is now connected directly to the source and actually controls the data being sent to the majority of the tree. And so if it decides to start dropping that data, the majority of the tree will be without the data and not receive the data the source is sending. So in order for the attacker to actually manipulate the structure of the tree, it simply manipulates the information it's reporting to its peer nodes. So it manipulates the metrics. It says it has good bandwidth, low latency, and a few children, and this results in a significant number of nodes actually connecting to it and requesting it to be their parent. So here we can actually see the effect of the attraction attack on ESM. So there are actually two lines here. The first line, being the black line, is actually a naive attack in which the malicious nodes simply drop data without trying to obtain advantageous positions in the network. And we can see that even when there are 30% malicious nodes in the network, they have very little effect on the overall performance of the system, and most of the nodes maintain 480 kbps. However, as the nodes perform attraction attacks in combination with just dropping of data, we can see that the performance of the system begins to degrade. And we can see that as the number of malicious nodes increases, the performance continues to degrade. We can see with 30% malicious nodes, the bandwidth is actually dropped to about 200 kilobits per second, or about 25% of what the system is actually able to perform. And not only does the performance of the system suffer, the stability of the system and the number